Wasn't sure what I heard over there. I'm a little groggy, just because I didn't sleep well, but you know. All right, another week. Woo! Any questions or concerns about stuff? Things you've noticed or wondered? Yeah.
How do goats climb up the walls? I saw a picture today.
That's awesome. How do goats climb up walls? All right. What do you think?
I don't. It boggles my mind. They don't use physics. Does physics just not apply to goats?
Physics doesn't apply to goats, yeah. They seem to defy gravity, right?
Yeah.
Well, let's see. In order to climb up steeper, I mean, if you're like this, you don't have to overcome your weight, right? But if you want to go straight up, you have to at least go up with a force equal to your weight, right? And initially, the upward force would have to be a little bit bigger than your weight to initiate a change. I find I like to use my arms a lot and point, but some people say use the board more, so here, I'll combine. The up and the down, they're balanced. If this is your weight, which we now know is your mass times the acceleration due to gravity, and this is a force of, you're pushing. If they're equal, you don't change your velocity, so you wouldn't get moving. So initially, this would have to be bigger than that. So you had a small net upward force to accelerate you. This is, I'm just trying to relate it to the class. But they are exerting a force. They're pushing on the rock, right? I'm not even going to try. Yay. Maybe some horns. Okay. Looks like a bad bug. Anyway, they do push down on the rock. And they would just slip if it weren't for what? Friction, right. Do you realize without friction you could go nowhere? You push against the floor, but it's supporting you. It's friction that pushes back. And that's what propels you. And so that's what's propelling the goats. So one, they must have good friction between their hooves and whatnot. And also, they have 4 legs to push to spread the workload out. We only have 2. So they're probably pretty darn strong. Because it is going to require a lot of force. And I don't know the typical size of a goat, but I don't know. Compared to a large man, they might weigh less. I don't really know that. Most goats aren't huge. So they don't weigh as much as us, so they don't need as much force. But they got 4 times the legs, and they're equipped for it better. But they do have to exert a force. If they slipped, they'd be toast. So I assume friction is a huge play. I'm not an expert, don't really know, that's my guess. We'd have to research more. Anything else? Other things?
I just had a question on the homework.
Yeah.
I'm still not sure what it means by, can you go back and reattempt a problem? Or, because it says 50% off for each
Yeah.
deducted if you attempt it beyond the first try.
Right.
You don't want to go back and retry.
Well, say there's 4 choices. Generally, I give you 1 less than there are. So if there's 4 choices, you'd have 3 attempts before it doesn't let you try anymore. Let's say the correct answer is A, but you don't know that yet. And you choose B. If you save your work, you don't know anything yet. It's just saved. But if you submit it because you're like, yes, I think it's B, go. It tells you whether you're right or not. You get a nice happy green check mark if you're correct. In this case, you'd get a red X. It would tell you you're wrong. But you could go back and have another choice. If you just leave it there, so be it. But most people go back and keep guessing. If you guessed this one, okay. And also, let's say this is 1 point. Well, you've now missed the 1 point. But you can get 50% of that if you get it right the next time. So we can still get a half a point instead of just a flat 0 if we can get it right now. Yay! If you miss it again, you get another X. And now you can still get 1/4 of a point if you get it right. But say you get it wrong again, Now you're going to get a 0 because, well, you blew it.
But that would imply certain problems, like, because if you have just a yes or a no,
You get one shot.
you get one shot.
Because you know the answer as soon as if you guess it wrong, then it tells you you're wrong and you know the answer. Which is beautiful because you don't have to wait for me to tell you what the right answer is. You know, and so you've learned right then while you're thinking about it. But yes, the less options there are, the less chances you get.
But it doesn't this applies to 4 options.
Or 3 or 7.
Okay, just more than 2.
Yeah, if there's 2, you get one less than there are, so you get one shot. I like that. I wish my homework had been that way. Good. Anything else? What made you think of goats?
Oh, I saw something on Twitter, like right before this class.
Oh, on Twitter, pictures. Well, that's cool. See, you're thinking. You're going to remember friction better. You know why we're on that? Let's do a friction demo, shall we? I'm ready for this. All right. You might have seen this on Mythbusters. It had been done a lot before them, but you know, they make it more popular. What they did is take a phone book and they interwove the sheets. So they're like that. And if you try to slide these apart, there is friction between them. There's weights of the top ones pushing down on the support surface, and so there's friction there. And if you pull it apart like this, it's easy. A lot of people think this works because there's a whole lot of friction like that. It's just because there's a lot of surface area. Excuse me. I did every other page. It took 2 movies. I redid it though, so it looked nicer. So then I just made these to clamp so you had a way to grab a hold of it. And I did put a flimsy piece of Scotch tape here just so it doesn't unravel. I'm confident people can rip apart a piece of Scotch tape. But see, it's just, there's no glue, there's no adhesive. The key to this is that normal force, that support force. Instead of holding them this way, if you squeeze them like this and try to pull, what I'm doing is squishing them together. And so it's pressing them together with more force. There's more normal force, and thus you think I'm, lying or something. Here, you grab that one. Squeeze, and we'll pull. And it's possible, but it's a lot harder. So I made a bigger version, obviously. Who wants to try it? Come on down. Let's have a tug of war. I need at least 2 people. All right, 1. We can have more if you want. All right, pull it apart. It's a tug of war. Well, at least they're even. So Mythbusters, they had the full on. Oh, come on.
So if we turn this sideways, will it?
Try it. They had 2 cars, and they still couldn't pull it apart.
Really?
Eventually, if you watch the episode, it ripped, but it actually ripped where it was being clamped. It gave here before they slid apart. I've hung from this. It was right here. I put that pulley over there, and I was just seeing, okay, is it going to hold me? It did, so I swung a little bit, and then I got scared, but Oh yeah, so it's tough. And it's just, as you pull it, there's a lot of friction there. And the stronger they're squished together, the larger that normal force, which increases friction. Now, forgive me, all of you of the Asian persuasion, but in America, these have been known as Chinese finger cuffs, which the Asians tell me, do you guys have these? Other classes, they tell me no. But you seen these before? You're supposed to squish it, stick your fingers in, and now you're trapped. I can't get apart. And the idea is as you pull apart, see how it squishes? It gets narrower in the middle there, skinnier. It's squeezing on your fingers harder. It's increasing that normal force, just like the phone book. And so there's more friction and you can't get apart without ripping it. So you carefully squish it and then you... But yeah, friction is a good retarding force. We had friction with air too, right? Air resistance. This starts falling. It accelerates at what rate? 10 meters per second every second. But this quickly, because it's light and has a lot of surface area, reaches, what's it called? Terminal velocity. Good. So its velocity is, what's it doing? When it reaches terminal velocity, what's it doing?
Constant.
It's constant. So the acceleration, the net acceleration on it is? Zero. Our force is acting on it. Yeah. The air up and the weight down, but they're balanced. And we call that equilibrium. And just because I've always loved these. Yeah. We have to throw it, it's with parachutes. So you jump out of an airplane, you're going to start falling. And you go faster and faster and faster and faster. And faster. But at some point, if you're going fast enough, the air drag increases enough to balance your weight. And you reach terminal velocity. You're still falling fast, but you're not going to go any faster. Whoosh. Just made that one. So, a question. A large person and a small person jump out of an airplane. Let's walk this through. Who's going to hit the ground first? Same time? Raise your hand if you think same time. All right. Who thinks not same time? Okay, most of you aren't voting then. You're not committing. Didn't make this a clicker question. I just thought of it. All right. Why do you think same time?
Because gravity is the same.
Good. Because we learned that the acceleration due to gravity is the same for all objects. I showed you that, right, with the ball and the feather? So this is one where I give you information, and I try to ingrain it in you. But we need to go one step further with this one. In real life, what did the ball and feather do? They hit at different times because we usually don't have a fancy vacuum, right? And because of the air resistance. So if you jump out of an airplane, in real life, there'll be air resistance. Consider that, and let's ask it again. Will they hit at the same time? Now most of you are thinking, no, you see, the other force is there. You're right. Without air resistance, they would hit at the same time. But there is air resistance. And if I forget to specify on any question, just ask me, because I didn't mean to trick you or anything. So, okay, who do you think will hit first?
The larger one.
Larger? Why?
He has more mass, his acceleration. He reaches terminal velocity faster.
He reaches terminal velocity faster.
So like if they're falling at the same time, eventually they will be going at the same speed, but he'll be further down because...
Eventually they'll be going the same speed, but he'll be further down. Yes? Add to that?
I think it's the opposite because
You think
if he
this...
reaches terminal velocity first, then he'll be going a certain speed before
So whoever reaches terminal velocity first no longer goes faster and faster. So in theory they can go together, but at some point one of them is going to reach terminal velocity before the other. Sounds like you guys at least agree to that. And the other one will keep picking up speed, right? Will go faster. And that one will get them ahead of the other person. One of them's terminal velocity is greater than the other's terminal velocity. But when they finally reach equilibrium, one of them will be going faster. Does that make sense? Which one? The larger. Because you have to be going faster to have more air resistance to counter the additional weight. So they'll both come to equilibrium like that. But for a visual, let's say this is the small person. The large person will be more like this. They weigh more, so they'll have to fall further, faster, before they have enough air resistance to counter. So because they're going at a faster terminal velocity, should get to the ground first. Cool, huh? Well, so at least when your parachute doesn't open, you know who's going to, whether or not you have to watch your friend go or you go.
Doesn't a larger volume of mass cause more air resistance?
Very good. Surface area, not surface area, cross-sectional area affects air resistance as well. A bigger area will have more drag, air resistance, than a small area. Yeah, for typical sizes, what I said will dominate, the weight. But yes, go like this and you at least fall a little slower. You've probably seen skydivers, they can do this, and they're falling slower to catch up maybe with their friends as they go faster. And then they'll to try to go the aerodynamic, less area to go a little farther. I mean, they're always going farther, but you know what I mean. Well, there, that was some fun friction ones. Okay. All right, more on Newton's second. No. Clickers. And hopefully it pops up without any problems. So far, so good. Come on, there we go. So in the bottom right, if you have a clicker, channel 41 still. If you have responseware, log in to that session ID number. And I'm going to ask some questions on what we've covered to help see if we were getting this in a way of review. So here's the first question. You can still log in if you haven't yet. Polling's open. You can begin answering. We haven't specifically discussed this one in class, but your book does a lot. That's why I chose this one. Here's our chance. So it makes sense to you. The train's going 8 meters per second. Sophia's in the train running at 3 meters per second inside the train. Well, what's her speed relative to the ground? Because both her and the train are moving with respect to the ground. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. We're going to get 46 responses today about, okay. Large majority of you think D. Either 11 or 5. Why both? Very good. It depends on which direction she's running. Let's say the train's moving that way at 8 meters per second relative to the ground. If she's going 3 respect to the train, she's now going 8 with the train and 3. The train's going 8, she's going 3, both in this direction. So they add to 11 with respect to the ground. But if she's running the opposite way, the train's coming at her, but she's trying to stay put. If she were running 8 meters per second in the opposite direction of the train, what would be her speed relative to the ground?
0.
Right, train 8, her 8, she could stay. It's like being on a treadmill, right? So that's why it could be either, and that direction matters. And it matters with respect to what? That you're considering things. You guys realize right now you're cruising along at, I forgot the value. So like 30 miles a second? I forget. Because the Earth is rotating. So we're whizzing around real fast. And the Earth is revolving. We got that motion too, but we usually don't have to deal with that because we're riding on the train. So we usually just deal with it with respect to the Earth, the train. But you're in motion right now, whether you realize it or not. Let's do another one. Whoops. I got to remember to hit escape while I'm in PowerPoint, not in Turning Point. That was my fault. Don't worry, I still have your responses. All right. Polling open. When a ball increases in speed by the same amount each second, what's that tell you about its acceleration? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey, oh, we gained somebody. Huh? 2 people. All right, most of you think 81 constant. That is the correct answer. It is C. Acceleration is the change in velocity. If you're not changing your velocity, it's staying constant. So if you increase the speed the same amount every time, you're falling 10 meters per second, and then 10 meters per second again, 10 meters per second after that. You're changing 10 meters per second every second. So it's constant, the acceleration. Questions? Does that make sense now? All right. 26 I wanted to do. Polling open. The acceleration of a raindrop that falls at constant velocity is. And we'll see if all that talk at the beginning of class made sense. Your response where? So are you logged in?
Yeah, but I have to.
Well, enter the session ID again then.
I did that like 20 times. I already signed and keeps kicking me out. That's the problem.
Keep trying. If it ultimately doesn't work, you're going to have to contact ResponseWare. We'll work it out. But email me. I'll give you credit for these. I know you're here trying these. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Large percentage of you, 81%, think it's 0. You're correct. So those of you that didn't get this right, if you're falling at constant velocity, that should be your tip-off. The velocity's not changing. So there can't be any acceleration. In this case, net acceleration. It is trying to be accelerated downward from gravity, but it's also trying to be accelerated upwards from air drag, air resistance. So there are 2 forces on it, but the net force is 0. There is no net acceleration. The acceleration of this raindrop is 0 because it's staying at a constant velocity. Does that help? Yeah?
So does that mean that if something reaches its terminal velocity, its acceleration at that moment is 0?
That's exactly right. And to repeat that, what's your acceleration when you start falling? 10. Yeah, that wasn't a trick question. 10 meters per second squared. But as air resistance builds up, what happens to that value? It decreases until it reaches 0 and you hit terminal velocity. So yes, at terminal velocity, your acceleration is 0 because you're not going to go any faster. You're still moving. Still going to hurt. But yeah. All right, I had one more. Go. Now free falling, that means no air resistance. So you can ignore air resistance when you're free falling. So at one moment you're going 30 meters per second. Exactly 1 second after that, what speed are you going? Now, see, you have enough info. Since everybody hasn't answered yet, I can tell you, some of you are still pondering. Is the speed changing? Yes. So that tells you what about the acceleration? It's not 0. It's something. Do we know what it is? I hope you do. It's free falling. What's accelerating it? Gravity. So we know acceleration is 10 meters per second every second. Every second, you're going to change your velocity by 10 meters per second. Wink, wink. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Does that mean you got yours to work? I'm going to guess yes. All right, 78% say C. You're correct. What would it be exactly? 40. Yeah, if you're going 30 meters per second at this point, 1 second later you're going to increase by 10 meters per second. So you'll be going 40. Because that's the acceleration. Yes?
So, quick question. In physics, they never use the term decelerate. They use the term accelerate in the opposite direction.
Good question. Yes, in physics, generally, they just stick with acceleration. But it's a vector. So which direction matters? We're used to saying, if we're going to accelerate the way we're going and speed up, we say we accelerate. And if we're going to slow down, we decelerate. That's still true. Just realize deceleration is negative acceleration. It's accelerating in the opposite direction at which you're currently moving. That's why it'll slow you down. But yeah. Questions, concerns? How do you feel? Ramping up for this test? Feeling good? Now you guys realize, those of you that have completed homework, when you complete it, you should know what the answers are, but I do add some little liners for clarity and explanations. I strongly encourage you, I mean that's why I do it, it's for you. Read those. Go look at the answer keys. That'll help you study. Yeah?
Could you remind us when your test is?
When it is? Yeah, it's on the schedule. But it's in a week, I believe. We're at the 26th, so yes, next Monday. Next Monday. We're in chapter 4 and 5 this week on Newton's second law and third law. We'll have a review Friday. Finish some things up and review. So come with your homework questions and things. You should know what you don't know by then, because you'll have me. And you can catch up on the weekend. Also, another warning that homework 4 on chapters 4 and 5 is not due Sunday night like it has been. It's due Friday night, so that you have more than just Monday morning to look over things. So this homework that you were able to start last week is due Friday. Yeah. Yes. This is all on the schedule in WebAssign, if and when you forget. Raise your hand if you've seen the syllabus, superhero paper instructions, and calendar PDF file in WebAssign. Raise them high. I hope so, or you guys are going to not understand what this class is about. Okay, good. It is there. You should be reading the superhero paper instructions. I'd like to discuss that soon so that some of you can start thinking about it and get going if you got questions. I know most of you are going to wait, but that way you have a chance. Well, we started Newton's second law last week. It's been presented to you. You guys were thinking ahead and already understand it. Quick review. So let's see, that's chapter 4, Newton's second. And again, when this whole class is over, I don't really care if you know which law is which, as long as you know what the laws are. What was the first one? That's good. Object in motion wants to stay in motion. Object at rest wants to stay at rest unless or until a force acts on it. And that's where the second law comes in. And the first law, we often refer to that as inertia. Newton's first law of motion has to do with inertia, that resistance to want to change its motion. It's happy the way it is. Don't mess with me, man. Second law is how the acceleration is proportional to a force. That's where you change its motion. So you push on something, you influence it, you're going to make it accelerate, thus change its velocity. That's what that is. And it depends on mass, but it's inversely proportional to mass. The more mass you have, the more inertia you have, the more resistance to change. So the heavier something is, for the same force, something heavy won't change its motion as much. And you knew that before you got into this class. This is just a guide to our thinking. And this is actually exactly equal in this case. And you can rewrite that as same thing, F equals ma. These are our guides to thinking and understanding all this. But now let's throw in Newton's third law. Anybody already know what it is? So I sum up while you're thinking. First one, inertia. Second one, F equals ma. Third one, has anybody read the chapter? Action, reaction. That's how I sum it up. And I bet almost all of you have heard the phrase, for every action, there's an equal and opposite reaction. And I've said that most of my life. So once I started teaching, I like to think of it as all forces come in pairs. Because for every action, there's an equal and opposite reaction. You can't have one lone force by itself. They come in pairs. You push on something, it pushes back. I touch you, you touch me. I'm pushing on the floor pushes back. And they're always in these pairs. And let's do a demonstration to help visualize that. I would need 2 more volunteers, pretty please. Any takers? Sold? Thank you. Come on down. All right, thank you. All right, if you have a seat here facing this way and you have a seat here facing her, crisscross applesauce. Get as close to the ends as possible because you guys are... Okay, what I'm going to do, and thanks by the way. See, who wants to be the wall? All right, you're a wall. Be a wall. So your job is try to stay as rigid as possible. She's going to exert a force against you. So when you're ready, put your hands on hers and give her a push. No. Oh. You're not supposed to push. You're a wall. Try it again. All right. Okay, you good? You fixed? You solid? Okay, give her a push.
She's so strong.
Come back. All right, this time you're the wall. Okay. Wall. Think Shakespeare. Was that one? I'm a wall. Chink. Anyway. Okay, you. Did you push?
No. Oh, wait, am I supposed to push against you?
See, I'm just playing with you. That's Newton's third law. You can't push without getting pushed back. You're trying not to push, but when she pushes on you, by trying not to push, you are pushing. It's equal and opposite. So the force you pushed on her is exactly the force you pushed back, and vice versa when you tried it. It even works if you were doing a rope. All right, you grab that one, and we'll start you guys apart this time. All right, you hold firm and fixed, and just give a tug. So see, they both moved. Very good. And my favorite way, all right, you can drop the rope. Feel that.
Oh, dear.
I don't like too many surprises, so if you feel that. All right. I want you guys to toss it back and forth among you as fast as you can. Good. All right, give him a hand. Thank you very much. I appreciate that. So, some force pairs. When she throws the ball, she pushes on the ball. So what's the pair, the force pair? The ball pushes back on her. Are they the same amount of force? Yes. That's Newton's third law. You push on this with a certain force, it pushes back with the exact same force. You can't get around that. Action, reaction. All forces come in pairs. Now you think, oh, the ball's smaller. It can't push as hard. Well, then you don't have to push as hard to push it. But however hard you push it, that's how hard it pushes back. Some things break. If you push too hard, they can only push so hard back. And if they can't withstand that force, they break. But that means they're not pushing back on you anymore, so you're not pushing on them. So it works out. So yeah, there's a force pair. She pushes on the ball pushes on her. Thus she recoils and started moving. And then likewise, she had to exert a force to stop the ball, right? So she pushes on the ball, but clearly the ball's pushing on her. Same force, and she starts going back. And then she throws it, another pair, and you saw what happened. Now, you guys are good scientists by now. Observations. Did one seem to move more than the other? Which one? This one? And please forgive me, I mean nothing by this. You guys, both of you are lovely. But you probably have different masses. And the one that has less mass, look what happens. If it's the same force on them when they push on each other, the one with less mass, less inertia, less resistance to change, will have a bigger acceleration. That's Newton's second law. So they'll change their velocity more. And she went faster a little bit. We could do it again with like the biggest person in the room and the smallest person in the room, but I bet you can guess what's going to happen, right? The big person will hardly move at all. But that's not because they're not feeling the same force, it's just because they have more inertia. You with me? So, you're tooling down the road. I grew up in Kansas. We had lightning bugs, June bugs. They were fun. It was at night. And one of my favorite ones was I'm going along in the rural, it's dark, and all of a sudden, splat! But while it was glowing, so it left this nice fluorescent green streak, chemoluminescent streak, for the next several miles. Who felt more force? My car or the bug? See, you're going to have to think about this more outside of class. I bet all of you are sitting here going, yeah, I got it. That makes sense. But you all just answered the question wrong. If the windshield exerts a force on the bug to stop it, it's the same force the bug exerts on the windshield. It's equal and opposite. It's a force pair. All forces come in pairs. So if the bug pushes on the windshield pushes back. Equal and opposite. Okay, felt. Touché. If the windshield had feelings, it felt it too, and it was the exact same force, same influence. But the bug has a lot less inertia, so it was accelerated a lot more, so much that it couldn't handle it. It broke. Here's another one. You're going to come around. I guess I didn't need to take that off. All right, bear with me. Most people tend to not like this one. Okay, I'm going to hit the ball. Ooh. I'm sorry, TLT. Okay, so I hit the ball. Who felt more force? We're animating it. We're personification, right? It's the same. Good. All right. Now I'm going to hit this. Who felt more force, me or the coffee filter? Same. Good. Good. You with me? Who felt more force, the ball or the coffee filter? If I swing the same versus... Not the same. Moo-ah. Look what happened. Who moves further? Yeah, the paper. The ball just kind of scoots a little bit. Their mass is clearly different. Their inertia is clearly different. This one gets accelerated more for the same force, yes. I'm trying to apply the same force to both. But this one gives way. You know, at some point I could maintain this, but I can only push on this as hard as it can push back on me. It's like the bug. If it breaks, it can't push anymore. If it gives way, it can't push on me anymore. Does that make sense? So what I'm getting at, this force pair is equal. But this force pair is less than that force pair. Because my fist and the ball can withstand more force. It can push back more than this can. One more example of that then is the wall. Any takers, volunteers? Who wants to hit the wall? You know who's going to break first probably? My fist. But I can hit it. I can hit it harder. I can hit it harder. And each time the force pair increases. I push on it with some force. It pushes back with an equal and opposite force. I can keep doing that until I can't swing any harder. It can keep pushing back with that, but I can't. Does that make sense? So at some point, one of the things gives, and it has to do with their mass and inertia. The structural integrity, if you will. Does that make more sense now? So we're going to use this a lot in this course. You're going to have forces. And we're going to get different types of forces as we go along. But Newton's third law always applies. They always come in pairs, and they're always equal. But they influence the mass differently. So, all right, there's my weight, 180 pounds. What's the force pair? Or just name some forces going on. Gravity, okay. Earth's pulling me down. It's trying to accelerate me, so it's exerting a force on me of 180 pounds. Okay, what's the reaction to that? Yeah, there's a support force. That is holding me up, and it's 180 pounds. Yes. But that's not the pair. Very good, very good. It's me attracting the Earth. So when you're doing these pairs, here's my clue for you, the cheat sheet. The pairs have to be on opposite objects, opposite bodies. If one thing pushes on another, then it pushes back on the first object. They're never on the same object. Does that make sense? The two you first said were Earth pulling on me and the weight pushing on me. So those two are balanced, putting me in equilibrium, but they're both on me. They're both affecting my motion. And in this case, they cancel. They are in opposite directions. They are the same magnitude, but they're both on me. So the reaction to the Earth pulling on me is me pulling on the Earth. I have mass. And so I influence the Earth just like all of you. I am pulling the Earth with 180 pounds of force right now. So next time you're feeling wimpy, just remember that. Whatever your weight is. But do we notice when I jump down? Ah! Do we see the Earth move? No. Why? Newton's second law. It's so massive, the acceleration I cause on the Earth is about this much. It is technically being pulled at 180 pounds, but we don't notice it. It's insignificant. That's the pair there. The pair is me running into this and it pushing back up is another pair. But me on the scale and the scale back on me. So notice they're on opposite bodies again. So they don't cancel each other out. A lot of people go, well, Newton's third law, things would never move because they're always balanced. Equal and opposite forces. I push on you, you push on me. Why would either of us ever move? They're equal and opposite. They should always cancel. That's because they're on opposite bodies. This one affects that motion, and this one affects the other object's motion. Thus, and I see you, when you're working problems and trying to think these through, those first force body diagrams, drawing the little pictures, try to find the forces on the thing that's we're trying to consider its motion. If you're looking at how the car moves, look at all the forces acting on the car, not the car pushing on other things. That won't tell you how the car moves, just the ones on the car.
If every single person on the earth...
Somebody always asks that. If everything, we all gathered on one side of the earth and could jump up simultaneously, would there be an effect? What do you think? Absolutely. Would it be significant? Absolutely not. Yes, we'd have a lot more mass, but there's a good calculation. Estimate how many people are on the earth with a typical mass, and now you know the mass of the whole population, all congregated on one side of the world. Now look up the mass of the earth. And so Newton's second law will say the acceleration will still be pretty darn insignificant. But there would be a measurable effect in theory. Yeah?
In the book, What If, the book about a bunch of like crazy hypothetical questions, he does that, and it's a more effect on the human population being all stuck in one spot, back out, and then moving on.
More effect from getting all of us in one spot. Yeah, absolutely. Yeah, all in there. Any last minute questions, though, concerns? All right, mull that over, and we'll continue more next time.